In the following presentation, I'd like to give you an introduction to lipid identification workflows in liquid chromatography trapped ion mobility mass spectrometry datasets within MetaboScape. MetaboScape is Bruker's all-in-one non-target data processing software, which covers all steps from raw data processing to high-confident compound identification. In the last release, we have focused on enabling high-confident lipid annotations in accordance to Lipidomics Standard Initiative guidelines. Therefore, I will present a full 4D lipidomics analysis workflow which covers raw data processing, statistics, automatic rule-based MS-MS lipid annotation, and, last but not least, graphically assisted manual data evaluation by using multidimensional Kendrick mass plots. So let us start at the beginning of this workflow, which is raw data processing. The idea of raw data processing is to reduce the complexity of the acquired dataset. MetaboScape comes with a collection of algorithms for various raw data types, including flow injection MRMS, multi-imaging, as well as LC-TIMS data. To achieve such a reduction of complexity, feature finding, de-isotoping, and adduct grouping algorithms are applied. The processing results are then collected in a so-called bucket table, which is displayed at the center of MetaboScape. A bucket table consists of multiple bucket rows, each representing a unique compound. All important compound characteristics, such as retention time, collision cross-section, mobility, as well as monoisotopic M/Z, are displayed at a glance. Based on the grouped adducts, which are also displayed in the bucket table, the neutral mass is calculated as well. A summary of all grouped ions, including adducts and isotopes, is stored for each bucket and can be observed, which enables full quality control for each compound. The obtained bucket table is the foundation of all further applied steps in the 4D lipidomics workflow. As the next step, I'd like to present some of the key statistical analysis features within MetaboScape. MetaboScape features multivariate statistical methods, such as principal component analysis, as well as univariate methods, such as the t-test. With only a few clicks, you can carry out one of these methods, as here shown for a PCA. The resulting scores and loadings plots directly appear below the bucket table. Using unsupervised multivariate statistics, such as PCA, allows you to find sample groups based on clustering in the scores plot. MetaboScape features the possibility to map your experimental design directly in the analysis software itself. For this, simply select the Groups menu in the top left corner and add as much groups as desired. Furthermore, for each group you can add various attributes. Once all groups and attributes are defined, you can assign those to your raw data files. The selected group and attribute allocation will be directly displayed in the PCA plot. In fact, all plots in MetaboScape are interactive to enable a rapid data exploration experience. As an example, you can select an outlying data point in the PCA loadings plot, and the corresponding compound is directly selected in the bucket table. I'd like to proceed now with the main topic of this presentation, which is automatic rule-based lipid annotation. Before I dive into what rule-based lipid annotation itself means, I'd like to give a brief introduction on the challenges of mass spectrometry-based lipid identification. The main challenge is the structural elucidation of lipids. Here you can see an example phosphatidyl-choline species. It consists of a choline head group attached to a glycerol backbone and two fatty acyl chains. Furthermore, one acyl chain contains a cis-directed double bond at position delta 11. When we now detect this molecule as an M+H ion with a modern TOF-MS instrument, we can predict the molecular formula based on the acquired accurate mass-to-charge ratio. This information alone leaves us with the problem that we cannot distinguish between occurring lipid isomers, for example here phosphatidyletanolamine 37,1. Next to isomers, also isobaric interferences from various formed ions in the electrosphere interface are creating an additional challenge. For example, in the case of PC species, the formation of sodium adducts. Many of these challenges can be solved via MS-MS experiments. For the here presented PC example, The observation of a head group fragment at m/z 184 allows a confident annotation on the so-called species level. At species level, solely the molecular formula in combination with the total number of carbon atoms and the total number of double bond equivalents in all acyl chains combined is described. If further characteristic fragments, such as neutral losses from the acyl side chains in positive mode, we can go one level further regarding the structural elucidation of our lipid species and annotate this species as PC160181 on the so-called molecular species level. This annotation gives us limited information on the molecular formula of the side chains, yet it does not provide any information on the double bond stereochemistry as well as the SN position of each chain, which is indicated by an underscores. So what can we learn from this PC species example? Lipids form class-specific fragmentation patterns, which we can store in rule sets, as seen for PC with the characteristic head group fragment 184. Lipid class-specific fragmentation patterns are better and better documented. Most recently, Tsugawa et al. Published an MS Atlas for lipids. That work is only one example of recent time. Similar projects, such as Lipid Data Analyzer and Lipid Match, have added to these pattern collections, only to name a few examples. To facilitate global communication between scientists, organizations such as Lipid Maps and most recently the Lipidomics Standard Initiative were founded. Especially the latter focuses on establishing guidelines along the full lipidomics workflow. One major aspect is the harmonized reporting of lipids. MetaboScape now follows the most recent update on the proposed shorthand notation for lipids by Liebisch et al. This nomenclature guideline for lipid annotation was designed for MS-based lipid analysis to avoid structural over-annotation. With MetaboScape, we are closely following the rapidly changing field of computational lipidomics with the goal to deliver a reliable, fast, and easy-to-use lipid annotation platform. Rule-based lipid annotation can be easily triggered in MetaboScape. The current implementation supports more than 40 lipid subclasses from 4 lipid categories. The scope of each lipid subclass can be adjusted by defining the range of total number of C atoms and total number of double bond equivalents in all side chains combined. The decision if a bucket is annotated as a lipid species is not only decided based on its MS fragments. In MetaboScape, we have implemented an annotation quality system that displays the accuracy of an annotation in one symbol. The scoring system includes MS1 accuracy, retention time, isotopic pattern matching, MS scoring, as well as CCS accuracy. Furthermore, for each quality parameter, 2 scoring tolerances can be added, one with a narrow range describing a very good match, and the other one with a wide tolerance indicating a moderate match. Therefore, next to the MS score based on the implemented fragmentation rules, we also consider the isotopic pattern as well as the MS1 accuracy for the overall lipid annotation. The lipid annotation can then be started by pushing the OK button. The overall annotation process for the whole bucket table will be carried out in less than a minute, giving the user constant updates on overall matched lipid IDs. Once the processing is done, you can start manual investigation of all annotations. You can get a fast overview for each annotation based on the AQ symbol, and in addition, you can inspect the ion traces of the features as well as the acquired MS spectra for each precursor ion. Manual evaluation of lipid annotations should be part of every lipidomics workflow. To assist this time-consuming process, we have implemented a 4-dimensional Kendrick mass effect plot in MetaboScape as a rapid graphical screening tool. So let me briefly introduce you to the concept of Kendrick mass effect analysis. In 1963, Kendrick himself published his idea how to reduce the complexity of petrolomics datasets. His idea was simple but very effective. He transformed the UPAC mass scale by redefining the mass of CH2 to exactly 14. This had the effect that compounds that solely differ in CH2 repeating units are having the same mass effect. This concept can be very useful to visualize lipids, since lipid species of the same class with different side chains occur in various organisms. As you can see in this theoretical database plot of phosphatidylcholine species ranging from 32 to 40 carbon atoms and 0 to 10 double bonds in both side chains combined, species that solely differ in the CH2 repeating unit appear on an horizontal line. Since most lipid classes also show a high diversity of species differing in their number of double bonds, a further interesting approach is to redefine the exact mass of hydrogen to exactly 1. Now, species that only differ in their number of double bonds are appearing on an horizontal line. I would like to show you now how we have integrated this concept of conventional Kendrick mass defect analysis into MetaboScape 2021 and our extensions of the concept by adding collision cross-section and retention time. Adding the retention time in form of a color scale allows the screening of false positive annotations by checking the plausibility of the retention time order. This is an example of a reverse phase chromatography method in which lipid species are separated by the polarity of the side chains. Adding the collision cross-section in a fourth dimension further increases the confidence of lipid annotations. MetaboScape can display the CCS value of each lipid species in the form of a bubble size of each data point, which allows further annotation plausibility checks. The 4D Kendrick plot in MetaboScape displays the whole bucket table. Using hydrogen as repeating unit reveals multiple horizontal lines of potential lipid species, even without adding any annotation information. All 4 dimensions of the Kendrick plot can be adjusted to any use case. For example, we can highlight all annotated lipid species by adding lipid class-specific color coding, or we can change the repeating unit to calculate a different Kendrick mass defect. All gray data points of the plot are not annotated buckets. If we now investigate single rows of already annotated buckets, we can see possible false negative results. This can have multiple reasons, for example, a bucket without an MSM spectrum, a too small scope of the applied lipid database, or simply too strict annotation tolerances. Since all plots in MetaboScape are directly linked to the bucket table, we can easily reanalyze this particular bucket with less strict annotation tolerances. In this case, the latter has produced the desired result. As a final example, I like to show how to use the 4D Kendrick mass defect plot for false positive annotation screening. The bucket table features various filtering options. You can go ahead and filter the bucket table by a specific annotation name, for example PC. The resulting Kendrick mass plot now displays smaller and more polar early lutein lysis species indicated by the blue color. Furthermore, they show a much smaller CCS value compared to PC species. To summarize, I hope I was able to show that MetaboScape 2021 is a user-friendly and powerful software to analyze lipids. Next to raw data processing and statistical evaluation, the key features rule-based lipid annotation for highly confident lipid annotation in accordance to the Lipidomics Standard Initiative guidelines, as well as the Kendrick plot analysis for data evaluation, will accelerate overall 4D lipidomics workflows.